Hopefully by now you've watched the crash course on the periodic table. I really like how they kind of go through everything and how the periodic table is set up. Kind of gives you a general idea of how they got to it. But we are going to talk about all of those properties, how it's organized, and those types of things. So the arrangement of the periodic table, right? The groups are columns. Those are things that have similar properties. So up and down, group 1, for example, has very similar properties, right? Those are the alkaline earth metals. Group 2 are the alkali metals. They all have similar properties. Group 7 over here is the halogens. They all have similar properties. Noble gases, similar properties, so on and so forth. Okay. Now, when we count the main groups, we usually skip the transition metals because they're all kind of the same. So we call these group 1A, 2A, and then skip the middle, 3A, 4A, 5A, 6A, 7A, and 8A. Those are the main groups. Okay. If you see them labeled as B, that's just counting completely from left to right. There's 18 because there's 10 of these, but we usually call this group 1, 2, and this one 3, so on and so forth. Okay. So the columns are called groups or families. The rows left to right are called periods. Those things actually don't have any properties in common. They're just all about the same size because we put them in order. So left to right, we do not have similar properties. Up and down, though, we do. Hopefully you learned a little bit about Dmitry Mendeleev. He set up the periodic table based on those repeating patterns and the atomic weight. So of course they are in order from atomic weight, smallest in hydrogen, all the way down to largest and whatever the largest one is now. And he went by repeating patterns, and that's how he was able to determine that we should have 8 main groups. So we should have completely 18 all the way across. And that's all based on those repeating patterns that still hold true. So what are those patterns and why does this pattern occur, right? It really has to do with those valence electrons that I mentioned earlier. Okay, so before I get into all of these specific periodic properties, you have to understand a couple of laws that govern how the electrons and the nuclei behave. Okay, the first law is called Coulomb's law. So if you've done any physics, you might have talked about Coulomb's law before. It's the same law that applies here, but really Coulomb's law is going to explain the trends and periodic properties, like I said, based on the number of electrons and protons. Reason being, electrons, which are negative, and protons, which are positive, attract each other, right? That's called an electrostatic attraction, positive and negative attract. So those types of attractions are what are going to explain all of these properties. Okay, so the attraction strength is based on 2 things. One of those things is the amount of charge, meaning if it's +1 or +2. So something that is +1 and -1 would have these arrows represent the force of attraction. A stronger attraction would be found between a +2 and a -2. Okay, they are more attracted because they have a larger charge. Okay, so the larger the charge, the stronger the attraction. Like between a 1 and a 2, it actually doubles in force of attraction. Okay, over here, the distance between the charge also affects how attracted they are. So if they're really far apart, like they are down here, this +2 and this -2, they're not going to have as much attraction as they are closer together. If they're closer together, they're going to be much more attracted. Think of them kind of as magnets, right? You have magnets close together, they're going to be really attracted to each other. They're going to want to hook up with each other. However, the further apart they are, they're not going to have as strong a bit of attraction. Same thing with the amount of charge. Bigger magnets are going to attract stronger than smaller magnets. All right, so both of those things play into Coulomb's law. So Coulomb's law really, like I said, explains almost all of the periodic trends we're going to talk about. So I have this little simulation that I'm going to show you. It's really small, but it really does demonstrate that force of attraction. So when we're talking about attractions, we're talking about a thing that's negative versus a thing that's positive, right? The electron, so this represents an electron, and this represents a proton, okay? So the closer they are, let's see, the force of attraction is 6.7 there. The further I move them apart, they have much less attraction. Now, if I change the magnitude of the charge, let's say I have like, instead of talking about electrons and protons, now let's talk about ions. So say this is a negative ion, like a Cl minus, and this is a positive ion, like an Na plus, okay? So those attract each other too. Now, if this is like a 1 and a 1, say these have the same level of charge, there we go. Same level, or close to it. That's close. Same magnitude of charge. So like +1, -1, I got a force of 1.3. However, let's say that instead of it being -1 and +1, it's -1 and +2. So I'm going to make this positive charge a lot bigger. Q2, right? I'm going to make it way bigger. Okay, so if this is +2, look at that, the force actually changed to be higher, 2.2. So the larger the charge, the more attracted they are. Okay, so that was Coulomb's law, which, like I said, explains all of the stuff that we're going to talk about. And it also plays into what's called effective nuclear charge. So effective nuclear charge is like how much strength or pull or attraction the electrons feel from the nucleus. Okay, so if you have like 6 protons, that's like a +6 attracting an electron. That's a really strong attraction. The more protons you have, the more attraction you have. However, some of the electrons, those core electrons, might be blocking that nucleus from attracting that electron really far away. So these are called the core electrons kind of shield, if you will, the electrons on the very outside. So if I have, what does this have? I think it's 1, 2, 3, 4, 5, 6. There's like, oh, that says +9. So there's +9 in here. That would be attracting an electron out here really strongly. Okay, the electrons out here. However, you have a couple of electrons in here in this blue area shielding the outer electrons from feeling that full charge of +9. So instead of it actually feeling a +9 attraction, you've got shielding occurring. So what you're going to do is subtract out the core electrons. So to get what's called the effective nuclear charge, or realistically, the nuclear attraction or pull on those electrons, you have to do just the number of protons minus the number of core electrons. So in this case, there are 2 core electrons. So you would do 9 minus 2. So really the electrons out here feel a +7 instead of a +9 attraction. Now that's a very simplified way of putting it. There's a lot more complicated calculations to calculate the actual attraction. But just know that the core electrons kind of shield the outer electrons from feeling the full pull of the nucleus. So that's called shielding. Core electrons block or shield the outer electrons from the full attraction of the nucleus. Like I said, for example, let's use sodium as an example. Sodium is number 11 on the periodic table. That means if sodium is neutral, it has 11 protons and 11 electrons. So each of those electrons would feel the pull of a +11. Now, there's actually 10 core electrons and 1 valence, because this is our shorthand version of sodium. There's only 1 valence electron out here. So we're going to talk about that 1 valence electron. It should feel a full pull of +11 from the nucleus. However, there's 10 core electrons blocking that outer electron from feeling the pull in the nucleus. So you do 11. Okay. You do 11 protons, your total number of protons, what it should feel, minus the 10 that are shielding it. So it really only feels a +1. And anytime you go to the next energy level, you've got a whole new level of core electrons. So this is kind of what it is. That 1 electron out there really only feels +1 because there's 11 protons and there's 10 shielding electrons. You don't have to be able to interpret or draw this, but it's kind of just showing you that, I think it says the density and then the distance from the nucleus. So the distance from the nucleus changes. You're going to have electrons feeling a different pull. And then this graph actually shows you like the number of protons, the atomic number, that's the purple one, constantly goes up, right? You add a proton for every element. But the effective nuclear charge, every time you go to a different level, energy level, anytime you have more core electrons, it jumps back down. See here, we go to the next level, that effective nuclear charge is lower. Okay, next level, sodium effective nuclear charge is lower and it increases as you go across. So like I said, that's going to explain some of the things that we see, but just know that those outer electrons don't fully feel the pull of that nucleus based on there being more core electrons than it.